1 Cl on this side. And here you have 1 Al. You have 2H. You have 3 Cl. So if you check, you have 3 chlorine atoms here, but 1 chlorine atom there. So what do we do to balance this? We simply add a 3 here. Okay. So now we have this 3 here, right? So why don't we add this 3 here? Why are we not adding it here and adding it there instead? Why is that? Well, because it's illegal to add a 3 here. It's not acceptable in chemistry. So you can only add it as a coefficient, which is this guy, not as a subscript, which is that guy. Remember that, right? Also, number 2, you can't obviously do this. You can't say H3Cl because you want to add the 3 next to the Cl. It doesn't work like that. Because this is hydrochloric acid and chlorine is part of it, you have to add it on the whole compound, which is where we just put it now, which is here. That's another rule, right? So this is the only allowed method of adding or trying to balance an equation, right? Now we have 3 chlorine atoms here and 3 chlorine atoms this side. But this means we now also have 3 hydrogen atoms on the reactant. Let's write it. Means now the updated version is 3H here. We still have 1 Al here. And we now have 3 Cl. Okay, let's update this side as well. Okay, this side is still the same. The products are still fine. Now, if you check our new numbers, we have 1 Al. Sorry, you have 1 Al, 3 hydrogens, 3 chlorines. Those are your reactants. The products, you have 1 Al, 2H, and 3 chlorine. So these guys, the H's, are not balanced. Right, before we move on to the next step, are the metals still balanced? We check our metals. Yeah, they're still fine. Als are still fine. Those are the only metals we have for now. So we move on. Balance H, which is step 4, right? Let's check our H. H is 3 this side. Please mute yourself. Let me see if I can mute you so that you don't disrupt the lesson. Just mute yourself there. Excuse me. I'll mute you. I think it's Lisiho. I'll mute you, Lisiho. Okay. Yeah. All right. So now, if you check our H, there's 3 this side and there's 2 this side. 3 on the reactants, but only 2 on the product, excuse me. So how do we make sure we get the equal number of H's on both sides? Well, what's our common factor here? Our common factor is 6, because 3 times 2 gives us 6. Right. So to make sure that we have the same number of hydrogen atoms on the reactants and products, given these odd numbers, 3 and 2, we can only relate them using 6. So how do we do that? We must make sure that on both sides of the equation, we have 6 H atoms. So how do we do that for the products? We simply put a 3 there. So 3 times 2 will give us a 6. So that's sorted for the products. Then we come back to the reactants. What do we do for the reactants? Obviously, we have to multiply this 3 plus by 2 to give us a 6. However, you write the 6 as is, not as a multiplier of 2 or whatnot. So you come here and you put a 6 instead. Aha! Right. So our H's are now balanced. So that means now, let me erase this. So with enough practice, you won't take too long to balance. For now, obviously, we're still learning. So going step by step it makes it look like this thing takes forever. It doesn't actually. If you are alone, you're not explaining to anyone, you're just moving. And with enough practice, it shouldn't take you too long. Okay, so now our new, we have AL, which is 1, we have 6H, and we have 6Cl. This side, however, we have AL, which is 1, and we have 3Cl, and then we have 6. Oh, let me make sure it flows. We have 6H, and then we have 3Cl. Aha. After balancing H, now we must check, are all previous steps still balanced? The answer is simply no. Why? Because we have 6Cl here and we have 3 here. Now we must find the common factor again to make sure we balance our Cls. So when going back to step 1, we check, are metals balanced? Yes. Are the non-metals balanced? No, which is why Cl must be balanced. So let's do it. What is the common factor of 6 and 3? So we have 6 and 3. Let me zoom in for you. So now we check, what's the common factor of 6 and 3? Well, 3 does go into 6, right? And 6 can be divided by 3 to get 2. So let's do this. The best way to explain this, if you have 6 and 3, and one of these numbers can be used to divide the other number, what you do is you take the smallest number, you divide the bigger number, and the number that you get is likely the number you would need to multiply by to get a balanced form of that equation, or of that element in this case. So we have a 6 here, we have a 3 here currently. Now we want to make sure we have an equal number of chlorine atoms on both sides of the equation. So in this case, it means we would multiply one of these chlorine atoms either from the products or from the reactants using A2. How do we do that? We come here, we check. If I multiply the products with A2, I'll get a 12. But then that will make my life difficult now, wouldn't it? However, if I come multiply here with that 2, I will get 6 chlorine atoms. Then my chlorine atoms will be balanced. Right. So this means now on the products, we have 2 aluminum, because remember, the fact that I put a 2 here, it multiplies everything in this compound, not just the chlorine atom only. So we have 2 aluminum. We still have 6 hydrogen, this guy. However, now we have 6 chlorine. Aha. So, remember what I said, sometimes you will try to balance. Sorry guys, let me mute and just close my windows there. Too much background noise. All right. Sorry about that, guys. Just make sure I had to get rid of the background noise. All right, let me share my screen again. Continue. Start now. All right, so where were we? Yes. Now, if you check, everything is balanced at this point because we were trying to balance H. That means we were at this step, right? Excuse me. However, we ask ourselves, are all the previous steps still balanced? The simple answer is no. We need to balance our metal. So we have to go back again to step one, right? And on step one, balance the metals. If you check, we simply need to add a 2 here because we had 2 Al now and we have 1 Al. So therefore now we have 2. So let's check the equation now. We have 2 aluminium, we have 6 hydrogens, we have 6 chlorines, we have 2 aluminium on the product, we have 6 hydrogens, and then we have 6 chlorine atoms. Congratulations, our equation is now balanced. This is the only time you would feel excited in an exam. The equation is balanced now. So what happens is in stoichiometry, this part is actually very crucial because it makes sure that if we want to calculate the number of moles, the concentration, and so on, we are actually calculating the right things because our equation does not. Oh, I almost lost connection there. Our equation does not neglect the law of conservation of mass. So if the equation is not balanced and you try to calculate your number of moles, your concentration, and so on, every value that you get there will likely be wrong because the equation was not balanced. It'll be an incorrect value. So how would this affect you in a real life situation? If you're trying to react certain chemicals, let's say you are a chemist and you want to say, I want to react hydrogen and maybe oxygen to get water, for instance, in whatever world you would do that in. If you have the false number or an unbalanced equation, you would react disproportionate amounts, if I can call it that. And then for every time you try to achieve your final product, you will never get there because your equation is not balanced. So when you were doing it in your paper or wherever, you did not balance it. So if I explain it to you in simple terms, if you are trying to get 10 burgers, but you are trying to achieve this with only 2 buns and 5 patties, you are in for disappointment. It won't work, right? So that's the simplest way I can put it. Because you would need 10 buns and 10 beef patties or chicken patties. I don't know what burger you prefer. Then you can make burgers. Right. Let's move on to our. I think we should do our last example so that we can move on to our other points. But this example was good enough. Okay. Let's say you want to balance. Okay, let's move on. If you want more examples, because obviously we have limited times in this lesson, always shout out on the groups. Or if you were doing an example by yourself and you realize that it's not really as easy as you thought, or you thought you understood but you didn't, you are more than welcome to ask. We will be happy to help you. Okay. Now, AL, let's try this example. Let's say you are reacting ion, Fe. There's so many of them actually that you can try. Fe plus water. And this should give you something like iron oxide and hydrogen. Yes, that should be fine. So, first step, always check, is my equation balanced? Because chances are you'll be told you are reacting sulfuric acid, or no, in this example, you are reacting iron with water to get iron oxide, and then when you write it out, it'll be like this initially. But maybe the next question might be calculate the number of moles. Before you move on to the next question, make sure this thing is balanced. So let's check it. Right. So I will be a bit faster than the previous step, than the previous example, sorry. So here we have one ion with 3 ions. Ooh, already we have an issue there. We have 2 hydrogens. Let me write it because it makes things easy. 1 Fe, 2 H, 1 O on the reactants, right? Product, 3 Fe, 2 H, and 4 O. Aha, these numbers mean the laws of mass conservation are definitely not adhered to here. So we need to balance this. Step 1, balance all the metals. This is our step 1, this guy. Balance all the metals. Iron is our metal. It's the only metal that we have actually. So let's see if we can balance iron. Let's put a 3 here. Right. We put a 3 here. That means our new ion would be 3 Fe. Right? And then we have 3 Fe on this side as well. Ah, good for us. Now let's balance the non-metals, which is our step 2. This guy. Balance the non-metals. Okay. But except O and H. However, in this particular chemical equations, there's no other non-metal except O and H. So what do? We move on to step 4. We balance the H first before we balance the O. Let's balance H. There's 2H here. There's 2H there. Ooh, our H is fine. No need to balance our H. Right? Now let's balance our O then. We have 2H here. We have 4 oxygen atoms, and we have 1 here because there's a 1 here. Right? So that means we can put a 4 there. So now we will have 4 oxygen atoms. However, putting a 4 there affects the hydrogen as well. So that means now we have 4 times 2, which is, let me write it for you, 8. 8 hydrogen atoms. But we have 4 oxygen atoms. Then let's come back this side. This side, on the product, we have 2 hydrogen and 4 oxygen. So these guys are balanced. However, this and that are not balanced. So let's go back here. We were trying to balance O, and now we check, are all previous steps still balanced? No. So we go back to step 1. We check the metals. Okay, the metals are still fine. We go back to step 2. We don't have anything except O and H. We go back to step. Okay, my steps were messed up here. I don't know what I did. Let me do this. This should be 3. This should be 4. Yeah. We go back to step 3. Is H balanced? H is not balanced. So what do we do to balance H? Since we put a 4 here, we can both see, or can all see, that we have 8H. And in order to get these 2 to be an 8, we simply need to multiply by a 4. Right. Remember what I said, if you can't do it intuitively, you had 8 and 2, right? You take the smallest number, you divide the big number. So you say 8 divided by 2, this will give you a 4, right? And you know that one of these, either the reactant or the product, must be multiplied by this factor, which is 4, in order to make sure that both sides of the equation are balanced. So in this case, we know that the one that must be multiplied by 4 is this guy on the product side, right? So at this point, we come back again and we do our accounting. This is the only time you'll do accounting unless if you're doing accounting as a subject as well. Now, you check 3FE, 3FE, you have 8H, sorry, that 8 looks funny, 8H, you have 4O on the reactants, and then you check the product. The product still have 3FE, you have 8H, and you have 4O. Oh, look at that. Our equation is officially balanced. Right. I would like to give you more examples, but for the sake of time, let's move on to our other point of today. So, what will typically happen is, let me do this. Balancing equations is actually a fun thing, by the way. So now I want us to actually calculate using balanced equations any of these, the molar, the volume, and the number of particles, any of those ones. So I have an example for you. Ooh, I had a, okay, let's do this. I have one example. Okay. Okay. Finding concentration. So let's do this one. Let's say you are given equation Fe. Let's use the very same equation. Plus H2O will give you Fe3O4 plus H2. Let me just take this one. H2. Okay. So let's say you are given this equation. In a problem, you won't necessarily be told that in order to balance these equations, you need to put a 3, a 4, and a 4, wherever we just put them now. You'll typically be given a scenario where they say you are reacting iron and hydrogen to get iron oxide and hydrogen. Sorry, iron and water to get iron oxide and hydrogen. Right. So Then you'd have to first balance it. Then the next question would be, if 1 mole, say 0.1 mole of Fe is dissolved in, say, 250 cubic centimeters of water, what's the concentration of the solution? Excuse me. So, what would you do in this scenario? If you remember, to find concentration, we always use the formula C is equals to N over V, right? You need the number of moles. We're already given the volume of the solution. And obviously, we want to find our C, which is our concentration, right? So, now, how do we go about it? We know that our number of moles is given in this problem, and we're also given volume. So, lucky for us, this was a straightforward problem. However, always make sure that this guy is converted to cubic decimeters. Always. Don't just take it as is. So to convert 250 to cubic decimeters, we simply divide by 1,000 and we will get 0.25 pm3. Okay, this looks funny. Now we are fine there. So then, therefore, C is equals to 0.1, which is our number of moles. Remember, we're just substituting in this formula, over 0.25. That should give you your answer. The answer is 0.4 moles per cubic decimeters. Now, it is very important to always include the units, otherwise your answer is incomplete and is therefore incorrect, right? The reason for that is if you don't include units, one day when you decide to become a scientist or an engineer, you will kill people, and you definitely won't like that. So units are very, very important. How you will kill people, let's hope you won't find out. Right. Now, that is how you would use a chemical equation that is balanced to find other stuff like your concentration, your number of moles, your molar ratios, and so on. So for the purpose of this lesson, we will do a separate lesson where we will go through all these problems, calculating moles, especially those ones that are in past papers, not these class examples, because past papers have more interesting problems. And then that should reinforce your understanding. Right, for now, let us just keep it here. This was just for me to illustrate my point. If we had this equation might be now we wanted to find the number right. The important point. So if we want to find the mass of this guy that is formed as a result of reacting the ion and the water, right? How would we do it? So since we have already been given the number of moles of Fe, we would have to take the ratio of Fe is to Fe 304. Why are we doing this? We're trying to find, because remember, in our previous lesson, I told you what these mean. This equation, how you interpret it actually, how you would say it in words, you would say, we are reacting about 3 moles of iron with 4 moles of water to produce 1 mole of iron oxide and 4 moles of hydrogen. Right. So if we react 3 moles, how much are we getting as iron oxide? So what we do here, we take the ratio. It's like saying if I have 5 buns, 5 buns is my iron, and okay, in this case, okay, 3 buns of iron, 3 buns, right? And 1 beef patty. How many burgers can I make? That's what we're trying to do here. So we have 3 is to 1. Why is it 3 is to 1? Because we have 3 ions and just 1. Let me do this. We have these 3, and here there's just the 1 here. Right, so that's what it looks like. We take this molar ratio. So now what we do as our next step, we take the one that has been given already, which is ion 0.1. We know the molar, the number of moles of ion that react, right? So this is assuming that ion reacts completely. So once ion reacts completely, how much of Fe3O4 will form? We don't know yet. That's why we're using the ratios. So the next step, you cross multiply here to find your x. Just solve for x in this ratio. So when you cross multiply, you'll get 3x, right? Because you multiply this and that is equal to 1 times 0.1. Then you solve for x. X is 0.1 over 3, because you divide both sides by 3, right? Okay, let me do it step by step. Divide by 3, divide by 3. So x is, what is 0.1 divided by 3? Should be 0.03, I think. Let's see. Yes, 0.03. 0.03 mole. What does this mean? It means for every 0.1 mole of ion that is used up, we form 0.03 mole of Fe3O4. So therefore, N Fe3O4 is 0.03 mole. Good. So the question was saying, what is the mass of Fe3O4 that is formed? Now, from this point, we know the number of moles of Fe3O4 that are formed. Let's see if we can find the mass. We know that N is equal to M over M. So the number of moles is equal to mass over molar mass. You can also use this triangle. Remember this triangle, it's very useful. The one that is at the top is here, and you have this guy, and you have M. So if you want N, for instance, you cover this, and it means N now is equal to M over M, right? If you want M, which is the molar mass, let's say you were given the mass and the number of moles in some weird scenario, you cover this. That means your big M is equal to the small m over n. But in this case, we're looking for the mass. That means we will cover the mass. And then it means to find the mass, everything at the bottom is multiplied. So you have m is equal to n times m. That's how this triangle works. It can work for any formula actually that has 3 terms and is a fraction. Even for this one, let me show you. Even for C is equals to n over V. You can have the same thing. You'll have the triangle, and you'll have an n here and a V here, and then you put the C there, right? So if you want the C, you cover this. You know that you divide n by V. If you want the V, you cover that, and you know that it's definitely n divided by V. If you want the n, seems like if you want the n, you cover the n and you divide, you're multiplying these ones. These are next to each other, you don't divide them, you multiply them. So the ones that you divide are the ones that are on top of each other. Right. So now to find the mass, we say m is our last step, is equals to n times big M. However, we know m, but we don't know big M. So big M of Fe3 or 4, right? We must calculate it first. Is equals to, we find the molar mass of iron. What is the molar mass of iron? We go to our periodic table. Where is iron? There is iron. 56. So it's 56, but there are 3 ions here. So it's 56 times 3, right? Plus, where's oxygen? Oxygen is here, 16. But there's 4 oxygen atoms. So it's 4 times that 16. What is our answer? Our answer is 3 times 56. It's about 118 and 168. And then 4 times 16, which the answer here, if you put it in your calculator, should be 232 grams per mole. Yes, if you were in our previous lesson, you would remember what grams per mole mean. Right, it just means for every one, let me see this. For every 1 mole of Fe3O4, we get that it actually weighs 232 grams. Yes. Okay, now we can find our mass. Therefore, our mass, we substitute here, remember we have n, which was 0.03, right? Times 232. And our answer becomes, what is times 0.03? About 6.96 grams will be formed. Good. That is how you would use balanced chemical equations to calculate your mass, your molar, your number of moles that are used up, the number of moles that react. So what it means is if our equation was not properly balanced, chances are here, when we find the final answer, the mass, we were going to get maybe something less than this or more than that. Maybe something like, let's say a mass of 3 grams or something like 9 grams. It was not going to be this correct one. So that's the importance of balancing equations. So when you get to your lab, you know that if I react about 0.1 moles of Fe, I will get about 6.96 grams of Fe3O4. Right. Okay, now let's move to the last part of today's lesson. Okay. Remember what we said, Fe3O4 is just iron oxide, right? So now, we want to determine, this is the easiest part of today's lesson, determining the theoretical yield and the percentage yield. This is actually usually given in one question. They don't separate them. So I have a typical example that I prepared. Let me see if we can do it fast. As our last example of today, okay, it should be here. So that you guys can see. Yes, good, found it. Now, we can just do this. Into that. Right there. And then, okay. Let's see. Can you guys still see my screen? I don't know. Oh, okay, let me do this. Start now. Theoretical. What was it? Theoretical. So what does it mean? Let's start there. In a lab, if you go to a lab right now and you try to brew something, say you're trying to react some hydrochloric acid with, or no, some sulfuric acid with ammonia and so on to get the fertilizer, like the example we're about to make now. What happens is before you go to the lab, you will calculate, right? Like what we were doing here. What we're doing here, we were trying to find that if we react 0.1 moles of iron, how much will we get as the formed product, which is iron oxide? And we found that we would get 6.96 grams. This means that in an ideal world where everything is perfect, we will get 6.96 grams. However, in our world, nothing is perfect. So you won't get 6.96 grams. Chances are, when you go to the lab to make this thing, to react iron and and water, you won't get 6.96 grams of iron oxide. You will probably get something less. The reason for this is maybe some of the contents are lost or they form some other unwanted products that we can't see. Or maybe they form gases that you can't see. And then as a result, some of that mass is lost. So you won't find 6.96. Chances are you'll find something like 5.2 or something less, right? But theoretically speaking, which is when you are calculating, you will find that you just need, you will get 6.96. So let me show you what it means. So now, your theoretic. And then actual yield. You see the difference. One of these is calculated, while the other one is what you would get as the value. So another good example is this. If you wake up, right, and before you actually wake up, let's say the day you go to sleep, you prepare that, okay, tomorrow I'm going to wake up at 7. Yeah, I want to be a good student. Okay, not 7, let's 6 a.m. Right, I want to wake up at 6 a.m. and shower, and by 10 past 6, I should be done showering. Right, so you write this down in your journal. So what will happen is, after you do that, that's your theoretical yield, right? Please give me a second, guys. Yes. Okay, we're back. Not sure if you can still see my screen. Let's do this. Okay. Seems like you can still see my screen. All right. So remember what I said. You the day before you go to your next class, you plan. Say it's 6 a.m. You write it down on your notebook or your diary. I don't know if you have a diary, whatever. Right. You write down. Okay, I want to wake up at 6. This is my timetable now. And 10 past 6, I should be done showering. By 6:30, I should be eating breakfast. That's your theoretical yield right there. That is the stuff that you predict. The stuff that you predict. You don't know if they will actually happen as are or as is. And then come 6 a.m. the following day, you just woke up at 6:05. Or worse, you woke up at 6:10. You see what happened there? You predicted that you're going to wake up at 6, but you actually woke up at 6:10. Now, the 6:10 time that you woke up with, that is in practice. That is in a real situation. That is your actual yield. It's the actual thing that happened. The theoretical one was your plan, where you were saying, if I can only wake up at 6. So that's the difference. If I can make, in an example type of, that's the difference between a theoretical yield and an actual yield. In a theoretical yield, when we calculate on paper, we say, okay, once you react 5 grams of iron with about 2 grams of water, and we expect, by our calculation, we estimate that we will get about 8 grams of iron oxide as a product. But when we get to the lab, the opposite of that happens. We react the same amount, of course, but now, instead of getting 8 grams of iron oxide, we get maybe 6 grams. So that is the actual yield. The 8 grams that we thought we were going to get is our theoretical yield. Right. That's the basic fundamental meaning of theoretical and actual yield. There's nothing more to it. So let's do an example as our last part of today's lesson. So before we do that, what ends up happening, the percentage is what we call now percentage yield. Percentage yield, therefore, it just tells you what's the difference between what you hoped to get and what you actually got. This is the actual yield over theoretical yield, right? I hope you can still see. And all of this times 100. That's how it works. So what is it saying, this formula? It's saying we want to see how far did we push to get to our actual to our expected value. So remember what I said, when you calculate it, in our case, this example, 6.96, right? 6.96 would have been our theoretical yield. And if we get to a lab and actually try to make this thing up, and we find that we get 5.08 instead. We would have to divide these two and multiply by 100 to see just how much of the expected value did we manage to achieve. So in this case, it would be 5.08. Let me see if I divide it by 6.96 times 100. That is about 72.99%. So that's your percentage yield. That's how it works. Actual yield over theoretical yield gives you a percentage yield. So it tells you just how much of your expected value you actually got. So you got 72.99% of 6.96 grams, right? So you couldn't get 100%. It's not possible to get 100%. So we always try to make sure it is as close as possible to 100%, because then we know we actually made more, right? So we didn't lose a lot. We try to make sure we don't lose a lot. So let's make an example. So this would be applicable as well. Let's say you are in a situation where, let's say you are selling soap and you actually make your own soap using, where's my image? Using whatever ingredients you use. And then you estimate that, oh, I will make about 10 grams of soap for every 3 or 4 or whatever number of grams I react. And therefore my profits when I sell this soap will be around 20 rands. If you make less percentage yield, it means your profits will also be less. Then that's where it would be applicable to you. Right, let's see this example. Aha, this is our last example of the day, guys. Then we can call it a day. So now, in this problem, sulfuric acid reacts with ammonia, right? To produce a fertilizer called ammonium sulfate. Right, let's write it down. This is what I was telling you. They won't always give you chemical equations. You'll have to, they'll give you this, and then they tell you the product is that. So these are my reactants, and those are my products. Let's write it down, because we are smart people. We know how to do this thing. H2, right? SO4. They say it reacts with ammonia. Ammonia is NH3 as given there. You won't have to memorize this in most cases. You'll be given the chemical formulas as well. You just need to know how to balance the equation at the end. So now our final product is ammonia. SO4. Aha. You see that? Let's see if I can do this. I think you can see that. You should be able to see that. So if you check now, these are our products, right? And these are reactants. So we have a full chemical equation that represents what we're doing at the lab right here to produce this fertilizer. Now, let's check first, is it balanced? Okay. Let's check if our equation is balanced. We have, because they won't always give it to you balanced. We have about 5 each, right? We have about 1s. We have 4o. Those are your reactants. Let's see products. Products, we have, and also 1n, nitrogen. Products, we have how many H's? 8. Ooh, interesting. And then we have Nitrogen. What sulfur? Sulfur we have 1. Oxygen we have 4. Nitrogen we have 2N. There are no metals in this case. So if there are no metals, we balance everything. We have to start by balancing everything else except O and H. So sulfur, lucky for us, is already balanced. Right. Remember our steps there? These ones. So we skip step 1 because there are no metals. We go to the non-metals except O and H, which is step 2. So we are at step 2 now. See, with enough practice, you will have it at the back of your head even. So another non-metal is N. N is not balanced, unfortunately. So let's balance N. We need to put a 2 here because we have 1 N this side on the reactants and 2 N on the other side. So, however, putting a 2 on this N affects the hydrogen as well. So now we have 6 hydrogen here plus these 2 hydrogen there, making it 8 hydrogen. And we have 1 S still, and we have 4 O still, but now we have 2 N. Let's compare it with the product. Okay, 8, 8, 1, 1, 4, 4. Sorry, this looks like a 40, guys. It's actually not a 40. It's oxygen. I don't know why I write it like a 40. Cool. Right. Aha. Seems like we didn't have to do much for this one. Everything is balanced. Right. Let's continue. What was the question saying? Now we can answer the question. Before we even go and read what the question was saying, let's first balance all the time. We can equation. Let's see. It was saying, what is the theoretical? How did N affect H? Okay. No. N did not affect H. So what I was saying is, I see your question. I hope it's not the. I'm not reading all the comments, guys. Let me see. Seems like you guys have been adding comments here. Okay. I only saw this one because it just popped up. Okay. It's only one person. Okay. Thank you for asking that. So how did N affect H? N did not affect H, right? So what we did is, remember, we were trying to balance, what was it? We were trying to balance N because we had 1 N here, not 2 N. But on the product, we had 2 N. So what we did, we came and put a 2 here. But whenever you put that 2 there, right, it won't only affect this N, it will affect the whole compound. So it will affect both the N and the H. So it will multiply the N, so you'll have 2N, and then it will also multiply the H. So you have 2 times this 3. So therefore you'll have 6H. Right. That's what I was saying. So remember, I've said it before as well. You can't put a 2 here and expect it to only multiply this H. It will multiply the H, the S, and the O. Right? And obviously, because we have 2 here, you will have 4H. You will have, since we have a 1 here, you'll have 2S. And since we have a 4 here, you'll have 8O. Because it's 2 times 4, 2 times 1, 2 times 2. Right? That's how it works. I think Ele, I don't know how to pronounce this name, Eli. Did I answer you, Eli, before I move on? You can just type there on the chat box. Thank you. Okay. She's answered. I'm very happy if you answered. Right. Now we can do the actual question, which is what this was about. So, what is the theoretical yield of ammonium sulfate? that can be obtained from 2 kilograms of sulfuric acid. If it is found that 2.2 kilograms of fertilizer is formed, let's break down this question. I'll even underline it for you. I'll use red. So 2 kilograms of sulfuric acid. What is that? That's the amount of sulfuric acid we are reacting, right? Now, it is found that 2.2 kilograms of fertilizer is formed. So lucky for us, they told us what the fertilizer is. It's just the ammonium sulfate. So they are saying after the whole reaction is finished, you will get 2.2 kilograms of fertilizer. I don't know why they're using kilograms here. So we'll have to convert to grams, right? We never use it as is. Okay. Now, the question is, what is the theoretical yield? We said the theoretical yield, you need the actual yield first, and then you divide it by the theoretical yield. All right, so let's see. The theoretical yield always, let me do this. The question is asking us to find this percentage yield, and we know the formula for that, right? So let's see, what are we given? Are we given the actual yield from the question? Yes, they said it's 2.2 kgs. Remember, the actual yield is what the amount of product that will actually be formed once the reaction is complete. But are we given the theoretical yield? No, we are not given the theoretical yield. They told us to find it. What is the theoretical yield? So let's find the theoretical yield. We were told that we are reacting about 2 kilograms of sulfuric acid. And we need to find how much how much this sulfuric acid will produce. We know that in a lab, we would get 2.2 kilograms. So in this case, they told us before going to the lab. So maybe let's say they did it months before, right? So when they did that, they saw that it could actually make about 2 kilograms. Right. So now they want to find what is the theoretical yield, the one that we would actually calculate before going to the lab. So let's find it. Before we do that, we know that the mass of H2SO4 is given as 2 kilograms. That's sulfuric acid. Now convert this to grams. Always, you don't work in kilograms in chemistry. Never. So this is 2,000 grams. Never ever use kilograms in chemistry. Always use grams. If you are given kilograms, convert. Now, unless it's specified otherwise, but just stick to grams. So you multiply kilograms by 1,000 to get 2 grams. Now, remember how we found the amount of product that is formed as a result of reacting the reactant. We have to take the ratio of moles. So we have to do the same thing here. But in this case, we were given the mass instead of moles. That means we must find the moles. So what are the moles of H2SO4? You use N over M, right? So we have, sorry, M, my bad, M over big M. We have the mass, but we don't have the molar mass. So let's find the molar mass. right? Molar mass. You go to your periodic table. 2 times 1, because hydrogen is just 1. What is sulfur? Where's our periodic table? Sulfur is 32. So we get 32 and plus 32, and we know that oxygen is 16. This will give us 2 plus 32 plus 4 times 16, about 98 grams per mole. Is it 98 grams per mole? Then we can find the number of moles of sulfur. So N of sulfuric acid is M over M, which is 2000 grams over 98 grams per mole. Some people don't substitute the units when calculating. They just use numbers only. Some substitute. It's up to you. It doesn't matter really. As long as you substitute the right units. Even if you didn't substitute them, you left them like just as numbers. It's still fine. As long as you made sure to convert everything. Even if you did this, it's the same thing. So what's 2000 divided by 98? 20.41. This is 20.41 moles. Good. Find right. I want to narrate it. Now, remember when we found the ratio of Fe to Fe3O4 so that we could see exactly how much Fe3O4 was formed? We do the same thing here. We'll say H2SO4. I should change color because everything is suddenly blue. H2SO4 is 2. We want to find how much NH42SO4 was formed. Is it the right chemical formula? Yes. When we check the ratios, it's actually a ratio of 1:1. Lucky for us. The ratio is 1:1. So we already calculated at the number of moles of H2SO4. So it's 24.41, which is this guy. My units are not very right here. It should be mole, not moles. Right, mole, like this. Right. Right. So this is the same guy that we put here. And now we don't know the number of moles of NH42O4, NH4SO4 that is formed. So we just put an X there. Is 2X. So we cross multiply. And since the ratio is 1:1, obviously it'll be 20. X will still be 20.41. Therefore, 20.41 mole of H is formed. Now we can find the mass of the fertilizer, the theoretical mass, because these are calculations. So therefore, the mass find the theoretical mass or yield. Now, how do we do that? Remember, N is equals to M over M. And from our triangle, if you like using the triangle, doesn't really matter. If you don't use it or use it, it's up to you. Since we're trying to find M, it means we must multiply N and big M. Therefore, M, N, and big M. So that is 20.41 times. We need our molar mass for this guy. Do we have our molar mass? No. So therefore, we must find molar mass. What is the molar mass of NH4? Right, it should be equal to, can you see here? Okay, it's fine. You go to your periodic table, you find nitrogen, you find hydrogen, and so on. Nitrogen is 14, hydrogen is always 1, sulfur is 32. So let's go back. Nitrogen is 14, but there's 2 of these here, so we must multiply like that. Remember, these things like this, right? These 2 multiplies this guy, and it multiplies the N as well. So there's always a 1 here. So these 2 will multiply the 1 that's there. That's why it's 14 times 2. Yes. Okay. So that's how it is. Now, it is always like that, remember. So that's why it's 14 times 2 there. It means here it's also going to be 4 times 2, which is 8. And the molar mass is 1. Plus sulfur with it is 32. Plus oxygen, which is 16. Right? Now, what will happen now? We'll have 28 plus 8 plus 32 plus 4 times 16. Right. So this is 132 grams per mole. So what is now our theoretical yield? M is Nm, which is 20.41 times 132 times 20.41. That is 2694.12 grams. Right, that is our theoretical yield. Let's go back. In our statement, we were told that our actual yield is 2.2 kilograms. Right, actual yield is 2.2 kilograms. Theoretical yield is the one we just calculated, which is 2.6. Because remember, 2,600 grams is 2.6 kilograms. So from here, you can basically say this is the same as 2.69 kilograms. So therefore, percentage yield, remember we said actual yield, theoretical yield, all of this times 100. Our actual yield, we were told that is 2.2 kilograms. You could have done it the other way. You could have converted the 2.2 kilograms to, actually, let's use that 2,200 grams, right? That was our actual yield, which is, where is it? This guy. This guy, the same as 2,200 grams, right? And we just found what our theoretical yield is, which is this guy, 2694.12. So we put it here, 2694.12 times 100. And that should give us 2200, 81.66%. That is our percentage yield, right? So theoretical yield over actual yield gives us percentage yield, always. Right. So that is our final point of today's lesson. Right. We have actually went above and beyond the time we're supposed to. So I will just cut it short and leave it here for today. And then if you have any more questions, please ask on the groups, please engage. And yes, don't forget to study and practice as much as possible so that you actually understand and fully immerse yourself in this, in these concepts. So that's it. We have covered that. We've covered that, and we were able to calculate the percentage yield of a chemical reaction. Thank you very much, guys. See you again on our next lesson. Okay. Yeah, at this point, you guys can actually go back and let me see this. Is this thing? Oh, yes. So at this point, we're done with today's lesson, guys. You can log out and yeah, go do your homework and take a shower, rest, do whatever really. And then we'll meet again next time. Thank you very much. And yeah, that's it. Okay, let's do this.